So I'm gonna have us get started here. Welcome to Dam Busters 2026 session number 7. Today I'm Lisa Kumpf and I'm the River Restoration Director at Charles River Watershed Association. Dam Busters is a collaboration between us, the Mass Rivers Alliance, and the Massachusetts Division of Ecological Restoration. This webinar series offers basic information about dam removal and is not intended to advocate for the removal of any particular dam or dams. For this year's topics and exact schedule, please visit the Mass Rivers Alliance website. Note there is no August webinar session, and our September session will instead be replaced by our free in-person conference on September 18th at Regis College in Weston, and we hope you all can join us at that. More details on the conference are available on the Mass Rivers website, including a tentative agenda and a solicitation for case studies. Soon, the Mass Rivers website will include conference registration information, so keep a lookout for that coming through your emails as well. Note that the deadline for submitting your dam removal project case studies for the conference is July 17th. So that's coming right up. So if you're thinking about putting in a case study, do it now so that we can coordinate those before the conference. And now for today's webinar, it is about hydrologic and hydraulic modeling. A few housekeeping items. First, this session is scheduled to end at 1 p.m. Second, please put any questions questions in the Q&A function at the bottom of your screen, and we're going to hold at least about 20 minutes for question and answer at the end. Note as well that these webinars are being recorded. The recordings and any other webinar materials will be made available publicly on the Mass Rivers Dam Busters website. And a final thank you to those of you who have been completing the post-session surveys. We will send out a survey link, as always, after today's webinar. Remember that you can win a Hydro Flask water bottle with the Mass Rivers logo on it if you fill out the post-session survey. And now I am delighted to introduce our speaker today, Rex Gamble, Water Resources Engineer from GZA GeoEnvironmental Inc. Rex joined GZA in June 2021 with a master's degree in biological systems engineering, and he specializes in stream restoration projects. The majority of his work consists of hydrologic and hydraulic numerical modeling for dam removal and stream restoration projects. Rex has served as the staff engineer and/or project manager on numerous restoration projects throughout New England, with his portfolio ranging from small, unnamed streams to iconic systems like the Charles River. So I will now hand it over to Rex to take over the screen and get started.
All right. Give me a sec to start sharing my screen. Oh. All right, so can everybody see my screen all right? Yep. Okay, well, thank you for the introduction. As Lisa mentioned, we'll be talking about H&H, or hydrologic and hydraulic modeling, with the little thing of understanding models and what they can tell us. So when it comes to objectives for this, it's a little bit more, I guess, basic. So it's more for folks who don't have as much familiarity with H&H, but we want to talk about some typical H&H modeling terms, the difference between hydrologic and hydraulic modeling, understanding different storms and floods, as well as typically used H&H models and packages and their application, how they can be used and what to choose, what model and when, and how to interpret some H&H results. As Lisa also mentioned, this slide recording and the deck itself will be available after presentation, so no worries about taking quick notes and everything like that. Okay, let's start with some H&H basics and terminology. First of all, what are the H's? The first H, hydrology, specifically in this case, surface water hydrology. There's groundwater too, but we're not going to talk about that. It basically tells us about precipitation and then runoff. In the end, it's all about the timing and amount of flow. And when you think about that, you basically have to think about a hydrograph. That's what we want from hydrology in the end of the day, is just a peak flow or a hydrograph. When it comes to hydraulics, it is stream flow characteristics once it's in the river or at whatever point of interest you're in. And when I say characteristics, I mean once the flow, the flood, whatever it is in the river channel, it's what is the flow depth, what is the flow velocity, what are the water surface elevations. That's what you're trying to get from hydraulics. So think hydrology is just flow, hydraulics is flow characteristics, depth, velocity, water surface elevations. Okay, basics. Let's talk about watersheds. So a watershed is basically the area of land that drains all its water into a common point, may that be a point in the river or a point in the lake. Watersheds are also called drainage basins or catchment areas. That's a phrase you're going to hear a lot used interchangeably. These watersheds are basically defined by topography. So that's the high points, hills, ridges of the land itself. The old school way of finding a watershed is essentially by getting a contour map from USGS and like hand marking all the high points around this one point. But nowadays, you can generally use computer software for that, which is very useful. So an example of a watershed on the bottom right is the Charles River watershed there. And you can see, I guess you can't see the contours, but it has a distinct shape, and all that area in this yellow on the bottom right drains to the Charles River in Boston. All right, so precipitation or rainfall. Generally, precipitation is defined by two characteristics, which is the depth and the distribution. The depth, which is just the amount of rainfall falling, generally can be found from NOAA Atlas 14 for a design storm. That's our general go-to. Essentially, you go to this website, you click whatever point you want to look at depth there, and it provides a point precipitation frequency table, which is shown on the bottom right there. And from that, you can get your 100-year, 200-year, 24-hour, whatever design flood depth you're looking for. So what's circled there is the 100-year, 24-hour storm. It's a very typically used kind of design flood. For this one point in Western Mass, it's 6.62 inches. So that's the depth. The distribution of the flood or of the storm is also pretty important. In Massachusetts, for design floods, we tend to use SCS Type 3, which is a nested storm distribution, but there are other ones available out there, but we'll not get too much into that. So runoff, essentially once precipitation hits the ground, it can either infiltrate or run along the ground. A runoff is the portion of precipitation that goes over land instead of infiltrates. Runoff is impacted by many things. In the watershed, it's impacted by soil characteristics as well as land use, but it can also be impacted by the precipitation characteristics itself, how intense it is, what the duration is, and the interplay between the soils and the intensity of the rain. But in general, we tend to use soil characteristics and land use to characterize how much runoff versus infiltration there is. And then hydrographs, they're essentially a graphical representation of flow rate versus time at a specific point in the river. So two hydrographs are shown on the bottom left and bottom right. Again, on the y-axis is precipitation and flow. And you can see in the orange line that is a flow hydrograph coming through after peak rainfall, which is shown in the blue bars here. And again, it's just a plot of discharge volume, flow rate versus time. That's all it's showing. And to get a little more complicated here, we can talk about statistical hydrology. It's basically a way of applying statistical methods to analyze hydrologic data, observed hydrologic data. So generally, it's looking for a flood frequency analysis, or you can look at base flows along those lines. So generally in the USGS maintains a bunch of flow gauges throughout the United States. An example of a flow gauge is shown on the bottom left there. For the most part, they measure water surface elevations or gauge heights and convert that into a discharge with a rating curve of some sort. So you get a giant flow record from, this one's from 1931 to 2025, long flow records. You get the peaks from that, and you can perform a statistical analysis on top of that and find like, what's the 100%, what's the 1% chance of a storm occurring? That's the 100-year flood. And we'll talk a little more about it here. So you hear the phrase 100-year flood a lot. So what does that mean? So a 100-year flood, generally people forget to say recurrence interval. So that essentially means that about every 100 years this flood will occur, but generally it doesn't have to be 100 years. It's what it's really saying is there's a 1% chance of this flood occurring every year. On the bottom left, there's an equation basically showing the relationship between this recurrence interval and the annual exceedance probability. So that's the probability of this flood occurring. And then on the right is a graphical representation of kind of a flood frequency curve based on some observed data. So for here, the 100-year flood, you can see that's defined in the x-axis by the return period on the top and the probability on the bottom. So it's a 100-year flood or a 1% chance occurrence. You mark that up where it intercepts the red line. You can go out to the left y-axis, and that tells you that the 100-year flood is about a little over 10,000 CFS. That's essentially what it's saying. So another example between the relationship is the 500-year recurrence interval flood is the 0.2 annual exceedance probability flood. That's all it's trying to say. It's a probability of this flow rate occurring with anything else. So another thing you hear a lot about in hydrology is regression or regression equations to calculate flow. Essentially, it's a statistical method, another statistical method used to define the relationship between different hydraulic variables. In general, for our analysis, we want to know what the peak flow rates are going to be based on watershed size and other variables. So essentially, USGS, again, they record a lot of data gauges all around a certain area, so let's say Massachusetts, and they look at the 100-year flood at every flow gauge. And then they basically try to perform a regression analysis to see at what size and what, let's say, soil percent sand in the in the watershed produces this size of flood. It's very complicated statistics, but all you need to know is generally you want to get a peak flow rate based on a watershed size and some other variable. And we'll talk a little more how to find this data later on. Okay, so now changing a little from hydrology into hydraulics, we're going to talk open channel flow. Basically, open channel flow is just any flow that is exposed to the atmosphere and is at the pressure of the atmosphere. So this does not mean pipes, anything that's pressurized in there, that's not what we're talking about. It's mainly open channels, may that be a natural river channel or even just a bucket, that's open channel. And we're generally two big variabilities or we talk about here. It is uniform and non-uniform flow, as well as steady and unsteady flow. I'll talk a little more about that in the coming slides. So uniform and non-uniform flow generally discusses the flow characteristics changing over time or not. So uniform flow are flow characteristics that do not change over, sorry, I said time, this is distance, over distance. An example of this is this river channel or simplified river channel on the bottom here. You can see flow is going to the right. At point 1, the flow characteristics are the same at point 2. It's the same depth, the same flow, the same velocities. Now let's say you build a dam here. That's going to cause some backwater behind the dam. And you can see now point 1 has a higher depth and probably a lower velocity than at point 2. And now this is non-uniform in terms of flow because point 1 does not have the same flow characteristics as point 2. So that's all it's saying. For the most part, almost every river system is non-uniform at this point because there's so much damming, so much culverts, so many road crossings, everything along those lines. So it's very hard to make the uniform flow assumption nowadays. So now let's go to steady and unsteady flow. So this is the same variability of flow characteristics, except in time instead of space. So steady flow assumes that flow characteristics do not change with time. So there's just one value and it stays that way. Unsteady flow characteristics assume flow changes with time. So this is a water circulation cross-section plot on the bottom left. If you run a steady flow model, all you get as a result is this dotted blue line, which is the steady water surface. But if you run an unsteady model, you get a water circulation that changes with time, which is what you're seeing there. It rises, hits the peak, and goes down to the bottom. or back down to base flow. That is a unsteady result. The same thing is shown in hydrograph form on the right. For a hydrograph, right, hydrographs are inherently unsteady because you're having a base flow going up to the peak, then going back down to a base flow. Steady flow, on the other hand, would just be just that peak, no variability over time. And then with open channel hydraulics, you hear a lot about 1D and 2D modeling. I should preface all this by saying that in real life, right, all flows, all of it is essentially three-dimensional, right? There's up, down, left, right, upstream, downstream. 3D flows described through some very complex differential equations called Navier-Stokes. Those are very hard to solve. So some very smart people a long time ago simplified those equations into something we can use down to 1D and 2D versions of these equations. And let's start with the 1D. So generally 1D assumes a difference or water's traveling only in one direction, which is upstream and downstream. In terms of left and right and up and down, it just takes an average of that. So this is primarily suited for in-channel calculations. And in general, when you do these 1D calculations, they're performed on a cross-section basis. So that's what's shown in the little plan view on the bottom left. It's essentially a calculation at every one of those green cross-sections. So it's not as many calculations as a 2D type of equation where you can see on the bottom right, where calculations are generally performed on a mesh at every cell interface. So there's a lot more calculations per time step for a 2D. So a 2D model generally assumes that flow is going upstream and downstream and left and right. In terms of up and down or in depth, it's depth average. So you still have a value there, but there's no difference between the bottom of the channel and the top of the channel in terms of velocity per se. And in general, 2D models are more suitable for very complex flows in an unconfined situation. So in a floodplain, for example, you get a lot more flow patterns, flow directions, and it's very good for looking at flow paths in that area. So H&H modeling. Essentially, what are H&H models and what can they tell us? Why do we build them? What are they trying to do? When it comes to this, I like to put it in the sense of H&H models are there to answer a question, right? Without something explicitly happening. So you want to know how this dam removal is going to affect flooding, but you don't have obviously the funding to do the dam removal right now, and you want to know how it's going to affect it. So you build a model to try and figure out or answer this question without actually doing the physical thing itself. It's just a representation of potential proposed conditions, existing conditions, all that sort of thing. And when you build a model, you essentially want to answer specific questions. A few examples of questions is erosion and scour. Is there going to be erosion and scour with this bridge pier? A model can help you figure that out. What is the velocity going to be? Is it going to be dangerous? How much flooding is there going to be? Is that flooding going to be hazardous? Those are questions that modeling can help you figure out. And explicitly for dam removal, aquatic habitat and aquatic fish passage is a very important question. And again, models can help you figure out how effective a certain removal geometry is for fish passage. So now we talked about modeling. I want to quickly go over some publicly available data sources you can use, because not every project you're going to have requires high detailed modeling, and not every stage. This is just very basic data that's available for the public and can be used to answer very easy early stage project questions. There's FEMA data, StreamSATS data, and USGS stream data, stream gauge data, as well as, depending on the project, past models and past reports. I'm going to go through each one of these and discuss what available data is around for these sources. So for FEMA, essentially, you can search up any community or any coordinate within the United States, and FEMA might have a model for that. Generally, when you look that up, you'll find either a FEMA flood insurance study, or FIS, or flood insurance rate map, or a firm. The FIS is essentially a report that discusses the methods, shows some profiles and the flows at this specific site, and then the firm is a visual representation of that in a plan view map. So this is an example of a FEMA firm at this Laurel Reservoir. One thing I do want to point out on here is that FEMA has a lot of zones, and in their legend, they define what these zones mean. So for example, a zone A, which you can see on the top in the reservoir itself, essentially means FEMA thinks this is subject to the 1% annual chance of flood, which is the 100-year flood. But it doesn't have base flood elevations available. So it doesn't have flows and it doesn't have elevations of the flooding available. However, zone AE, which you can see in the river channel south of the dam, it is subject to the base flood elevation, and FEMA has these flood elevations and flows available. One other thing to point out here is this hatched area, which is the floodway area. That is a very important area in terms of permitting. If your project takes place within a FEMA floodway, then some sort of further FEMA analysis, no rise, or even a CLOMAR if you're causing a rise, will have to be performed, and we'll discuss that a little more later. So this is a FEMA firm. Next, we'll look at the FEMA FIS, which again is the report that kind of accompanies a firm. It essentially discusses the methods of the model, flows, and then provides some results. So this is a FEMA firm from Fairfield County in Connecticut. We're looking at Laurel Brook, and you can see here for this site, they have the 10%, 2%, 1%, 0.2% chance annual exceedance flood discharge values for this. So for the 100-year flood, which is the 1% annual exceedance chance, the flood volume is about, or peak flood estimate is about 5,100. So that's very useful data when you're starting out a project to start assessing feasibility or just trying to see how flooding is at the site. And then on top of that, the FEMA FIS also has flood profiles. So they have their own models that they run, and then it provides elevation profiles. As you can see here, there's the, again, 0.2, 1%, 2%, 10% chance flood profiles here. And again, might be a good starting point for a project to assess this data. Another public data source is StreamStats. It's a web application maintained by USGS. It essentially relies on this regression equations that we discussed earlier to estimate stream flows at ungauged sites. So you basically go to the USGS site, you zoom in on a certain point, and these blue lines pop up. Those essentially represent stream channels. You click on a blue line and it delineates the watershed for you and then provides peak flow values, base flows, whatever you might want, or I guess whatever data is available at the site. Again, it's a very useful preliminary tool, publicly available, very user-friendly, but it is not a rainfall runoff model. It only provides peak steady inflows or flows to the site. And finally, there are stream gauges that are publicly available. As you mentioned, USGS maintains a bunch of stream gauges throughout the United States. When you click on one of these, you can see what data is available. Generally, it has discharges as well as gauge heights available. May that be for every 15 minutes continuous data, daily data, as well as peak stream flows from whatever year it started recording to the present or whenever it stopped recording. It's a very useful interface. We're going to talk about the statistics of analyzing this later. Just if you use this data, make sure you're aware of its limitations and how to analyze this data for, I guess, statistical hydrological purposes. All right, so now that we've gone over a few public data sources, let's look into more, I guess, softwares and models we can apply for both hydrology and hydraulics. So hydrologic models, there are many different types and there are many different methods. We've discussed maybe 3 different methods so far. There's regression method, there's gauge analysis, and then there's rainfall runoff modeling. So regression equations, again, available through StreamStats. Gauge analysis is site dependent, depending on whether USGS has a gauge nearby, but you can analyze that data with USGS peak FQ or HEC SSP. And then rainfall runoff modeling, again, is converting precipitation depth and distribution into a hydrograph stream flow. There are many different types of models for that. The most commonly used in rivers anyway is HEC-HMS, which is a publicly available hydrologic model from the Army Corps of Engineers, but there's also HydroCAD, which is very frequently used, especially in stormwater contexts, and TR55. For hydraulic models, and many different types available. There's a bunch of examples here, including HEC-RAS, which is a, again, very frequently used, publicly available model developed by the Army Corps of Engineers. And there's SRH, another river or culvert-focused type of model. Culvert Master, HY8, again, very culvert-focused models. And then there are just typical empirical equations. So think of Manning's equation. That's, in a way, a hydraulic model. And you can choose 1D, 2D to simulate flow through here. You just have to essentially assess what's most appropriate for the site, which we'll talk a little more about later on. We also want to note that there's combined hydrologic and hydraulics model. They're frequently referred to as rain on grid models. Essentially, this does hydrologic and hydraulic calculations on a mesh. So this is an example on the right of a rain on grid model working. The model essentially applies precipitation directly to a grid, performs infiltration and runoff calculations per grid, and then routes it using hydraulic equations. Because this is a 2D model doing calculations on every grid face and every grid, these are very computationally intense, or effort has a lot of computation effort. It takes a long time to run, so they're not always a go-to for a dam removal type project, but they're becoming very common in stormwater projects. Examples of models that do this are HEC-RAS and PC-SWIM. And we're not going to talk too much about this, but there are specialty models, particularly scour models and sediment transport models. So essentially, what these models do is they have an extra layer of calculations on top of a hydraulic model or a H&H model to either estimate how much scour there's going to be, how much movement of sediment there's going to be in a channel. But I'd be very wary of jumping to these type of models, essentially because they tend to be, again, very input intensive as well as computationally intensive. So know that these models are available, but I wouldn't jump to them as a go-to for, I guess, any type of dam removal unless you need to for a very specific type of project. Okay, so I gave you a lot of options for publicly available data, models, or H&H models. How do you choose? And again, I think it comes back to the question of what questions you're asking and your desired output. The level of detail you might want, as well as your project goals, again, which relates to the questions. And then a final thought is budget and funding. So for one, if you just want to know how much flow is coming into a site, you just need to know peak flow rate, then all you need is a hydrologic model. You don't need to think about a hydraulic model. But if you want to know characteristics of the flow at the site, such as depth, velocity, then you might want to opt for a hydraulic model as well as a hydrologic model. There's the options of steady and unsteady. In this situation, a unsteady model would probably be needed if you're trying to assess something like flow retention or flood retention and how much a flood is going to dissipate either with a dam removal or adding a dam or with wetlands in the watershed or in the reach. That is when an unsteady model would be useful, because an unsteady model doesn't account for those changes in flows over time with this being flooded or that being flooded or the dam being removed. So that's pretty important. And then I think I mentioned this before, but when it comes to uniform and non-uniform models, pretty much every hydraulic model you're going to have now is non-uniform. The only uniform type of model I can think of is a Manning-Zen equation. It doesn't really account for changes upstream and downstream. It's just within the cross-section itself. So I'm going to talk a little more about these, but one thing I think we should really get into is looking at the output of these type of models to determine whether it's going to answer your questions or not. So looking at hydrologic models, again, there's a question of whether you need a steady or unsteady output for these. If you just need a steady flow, then a regression analysis or a gauge analysis is perfectly reasonable. However, if you want to, again, potentially assess different flood retentions, you need a unsteady hydrograph, and that's when you want to apply generally a rainfall runoff model to assess how flow is changing over time and changes to flow through your region. When it comes to hydraulic modeling, there are a bunch of different outputs, so we'll go over a few of them. One of the most common outputs you're going to see is a longitudinal profile or hydraulic profile. Essentially, it just shows how the water surface elevation changes with space. This is an example from a 2D model here. On the bottom left, that's our output, and the pink line shows the profile we're going to plot, which is then shown on the right. And as you can see, at station maybe 380, there's a dam, it's causing backwater, and then downstream of the dam, you can see the hydraulic profile is a little more uniform, but that's just an example of a hydraulic profile output. You're also going to get inundation areas and depths. That is pretty useful information. So it's a visual representation of water depths at various points in the river system and your model. You can find maximum, minimum, and a range of depths within the flood. The same thing, you can find the same thing for velocities. Again, this is a plan view of some velocity results. Essentially, the color palette reflects the magnitude of the velocity here. And what's also very useful, especially with much 2D models, is you can find particle tracing, which is these, as you can see on the bottom right figure, these blue squiggly lines essentially showing the direction of flow. And one last thing we want to discuss when it comes to modeling output is assessing how, I guess, reasonable or how accurate your model output is. And if you really want to kind of dig down and dive in to get your model very accurate, you might want to consider doing some calibration and validation. So calibrating a model is essentially adjusting model input parameters to produce the results or produce results that match observed data. Validation is another step on top of that where you're running your calibrated parameters to check against a different data set of observed data. So you would need a certain amount of available data for this to be possible. For one, you need observed precipitation, then you need observed stream flow. And then for calibrating a hydrologic model, if you want to calibrate a hydraulic model, then you need observed high water marks or observed watermarks from a flood that actually happened, or just from base flows you can look to. But I would always recommend, if you're modeling for a flood, getting high water marks from a flood. If you're modeling for base flows, get observed base flows. One thing I do want to say is that this is not possible in many cases. Like I said, you need that available data there to be able to do this. So it is very useful and very good, but it's a lot of effort and it may not be possible. So this is an example of a calibrated hydrologic model. Essentially, we got the historic modeled flood or for precipitation from radar data, and then we plugged it into our developed hydrologic model. Our observed stream flow here is in the black on the bottom right, and then our model stream flow is blue. And you can see our hydrograph reaches our peak and goes down. The shape is pretty adequate, so we thought this was a decent calibration and moved on. For an calibrated hydraulic model, this is an example from HEC-RAS, and we had to basically get high water marks from USGS. I believe this is actually from Tropical Storm Irene. That is represented by the little red blips in this longitudinal profile here. That is the observed high water marks for this flood in Western Mass. Then we modeled this same Tropical Storm Irene in our HEC-RAS model, and this is the output profile. And you can see with a little bit of calibration that our water circulation hits these high water marks pretty accurately. So we're pretty satisfied with how this model was calibrated. So coming back to the question of how do I choose a model, we have a few examples, and I'm going to go into a further example later. But let's say you're doing a culvert replacement and you want to reduce overtopping because the culvert is undersized. The question here is what size culvert is going to pass the 50-year flood without overtopping this roadway, right? So when we want to answer this question, we need a hydrologic model to estimate the 50-year peak flow. You can do a stream stats, you can do a HEC HMS, you can do a gauge analysis. All those are appropriate methods for answering this question. And then to get the water surface elevations through the culvert or over the roadway, you have to develop a hydraulic model. You can use a culvert-specific hydraulic model like Culvert Master or HY8, or you can develop a 1D HEC-RAS model. Our example number 2 is we want to remove a dam and we are very focused on fish passage. So our question is, what channel floodplain geometry will have the appropriate depths and velocities to allow for fish passage? In this case, for the hydrologic modeling, we need some sort of base flows because that generally when fish passes through base flows rather than the floods. So we're going to perform some sort of gauge analysis to get that. Or you can do stream stats and use regression equations, but gauge analysis is available. So that's what we did. And then because we cared a lot about the spatially variable depths and velocities in the channel and in the floodplain, we're going to use HEC-RAS 2D so that there's variability in both left and right, as well as upstream and downstream. So now we kind of have a basic grasp and a few examples. We're going to add another layer of complexity on top of how to choose a model, what's the best type of model to use. And there are other type of things that are going to influence your model choice. So model choice is influenced by project stage, your permitting, our regulatory agency, as well as the funding available. So for one, the type of model we're going to use is going to vary depending on if you're doing a concept level or feasibility level study versus a final design study. You might want something a little more nitty-gritty and provide more detail for a final design study, for example. The type of model you may use might be influenced by your review agencies. May that be MEPA, FEMA, or MassDOT. We'll discuss that a little more later. And then the funding source itself, certain funding sources might have certain requirements for. So just to get kind of a sense of, I guess, low effort, low cost versus high effort, high cost for hydrologic modeling and hydraulic modeling. For hydraulic modeling, let's say you're early on in a project, it's a low cost feasibility type study, you might want to just use FEMA flows and stream stats. That will get the job done. That's all you need. And then you might want to pair that with a very simple 1D steady model, maybe even the FEMA model that is publicly available. But let's say you're further along in the project and you have a little more budget now to do some more detailed modeling and you have more, I guess, questions to answer. You might want to pivot to a HEC HMS model to see if there's going to be any changes in flood retention with the dam being removed. And then you might want to use a 2D model to assess fish passage or the velocities near a bridge upstream along those lines. So this is just a decent representation of, I guess, how much effort versus how much high effort, what's a high effort and what's a low effort model in this sense. And then one thing I do want to note here is that any calibration of either H and H model is going to require more effort and more time on top of all this. So let's talk a little about how your review agency might affect what models you use. For example, certain ecological projects, dam rules, usually ecological projects, may qualify for a MEPA exemption. If that were to occur, then you could bypass the MEPA review process and you could have a little more flexibility with what type of modeling you want. But if you have to go through the MEPA review process, then that requires you to use the Resilient Mass Action Team, or RMAT, guidance. Essentially, it's a website you go to, you type in your project characteristics, what it is, the funding, the potential effects, and it'll basically spit out a bunch of tiers and considerations you might have to consider, I suppose. That may include future precipitation, how you model, and it basically just provides a bunch of projections as well as a bunch of methods it wants you to fulfill to get through this MEPA process. Another really big sticking point sometimes is FEMA. We discussed looking at a FEMA firm before, and I quickly discussed model being in a floodway. So if your project is in a floodway, then you have to at least go through the MEPA or the FEMA process and look at whether your project is a no rise or causes any rise in the stream. FEMA has a very specific set of modeling methods and reports that it wants you to provide for this no-rise analysis. If no-rise is shown, then you can send that to local authorities and that could be set. But if a rise is shown, then you might have to perform a LOMAR or a CLOMAR to show that this flooding is not going to affect any nearby properties or endanger anybody's life. But like I said, when this is happening, you have to essentially consider the type of modeling that FEMA prefers to look at, which is generally a 1D hydraulic model using FEMA flows. So with all that complexity, I think we're going to try and end this with an example project. So this is a real project that GZA performed for a dam removal in Monson, Mass. It is a former industrial dam that has no use anymore. The aim is to remove the dam, reconnect the floodways, and then limit sediment transport from the impoundment downstream. In terms of constraints here, we had some real worries about some retention walls on the upstream impoundment and how lowering the impoundment and then potential head cutting upstream will affect those walls. This was in a FEMA floodway, so we had to perform a FEMA no-rise. And then there are issues about, there are a lot of pressures and limitations in terms of sediment movement downstream. That was a big concern, as well as whether this is appropriate for fish passage. So when it came to this, our questions, our H&H questions were pretty much, will removal increase flooding downstream? Big concern. Does the removal geometry re-impound water during a flood? So if the removal is performed, we don't want the impoundment to basically fill back up with water during a flood and become a hazard again. We have to make sure that doesn't happen with our removal geometry. Another H&H question is, will the removal affect nearby infrastructure? And then does the removal allow for fish passage? Those are our 4 big H&H questions. And I think these are pretty common H&H questions when it comes to dam removals in general. So when it came to the project being removed, we did use publicly available data to start with. We looked at FEMA, we looked at stream stats, we looked at publicly available LiDAR. But because of a lot of permitting and a lot of requirements on that front, we also had to perform our own modeling as well as collect a bunch of data in the field. Site-specific data we collected included topographic and bathymetric surveys, sediment sampling, probe depths, and then a bunch of wetland waterway habitat surveying. But in the end, in terms of H&H, we performed a gauge analysis for this. We performed a HEC-HMS model. So we made a HEC-HMS model and calibrated it a little bit to the gauge analysis. We actually performed both a 1D HEC-RISE model for the FEMA no-rise. And then when we got further down into the project, into the design phase, we found that the 1D model essentially did not have the spatial resolution we wanted to look at fish passage, to look at potential velocity changes in the impoundment. So we developed a 2D HEC-RISE model to answer those questions. And when it came to these H&H questions, will removal increase flooding downstream? Our models showed no, it won't. And that was shown in both the 1D and 2D model, initially the 1D model. Does the removal geometry re-impound water during flooding? It showed that we didn't. So during the 100-year and the 500-year flood, which are significant from a permitting perspective, we showed that the impoundment did not refill with water and become a hazard again. Does removal affect nearby infrastructure? We found that yes, when you remove the dam, it increased the velocities in the impoundment and increased the velocities near those retention walls we're very, very worried about. So then we had to go back in and using our model output, we could estimate velocities near those walls and size scour protection for those walls. And then finally, does our removal geometry allow for fish passage? We had to look at some gauge flow for this, model some very small base flows in the channel, and look at the velocities and the depths. And we found that our species of interest, which are trout, could pass this under most base flow conditions, including the medium base flows during upstream migration season. So that kind of summarizes a lot of what we want to do with the example project. And I'm going to end with some key takeaways. So for one, H&H means hydrology and hydraulics. Hydrology specifically refers to flow timing and magnitude. Hydraulics refers to flow characteristics once it's in the river, so depth, velocities, water translations. Some common public data sources include FEMA data, may that be the FIS or the firm, USGS stream data, as well as USGS stream stats. Typical softwares for hydrologic modeling, HEC-HMS is, I would say, the most common hydrologic model, but HydroCAD is also very common. And then for hydraulic modeling, HEC-RAS, I would say in the United States anyway, is the most frequently used hydraulic model. But you might want to have a little thought into whether you want to use a 1D or a 2D, depending on your questions again. And then the level of effort of your model and of the project in general is dependent on many things. That includes the project stage, the complexity of the site, regulations on top of it, and regulatory agencies, the available data, as well as the available funding and budget. So when you make a model, we just essentially have to make sure your model outputs match your intentions and your questions coming into the project. And that's going to vary a lot, but that's very important to consider as you go about choosing H&H models and applying them. If that comes to the end, I think it's now question time.
Yes, thank you so much, Rex. And please, if you have questions, put them in the Q&A box, which you can find at the bottom of your screen. Or you can raise your hand and unmute. I guess I'll start off with one question is for dam removals, in particular, what type of approach for modeling do you typically go to kind of in the feasibility phase and then in the design phase?
Sure. So I think in the feasibility phase, applying gauge analysis is my go-to, as well as stream stats. Using multiple methods isn't bad in comparing them, especially for bigger river systems where flows tend to change less, especially at the flooding. So for example, in the Charles River, right, a flood can be a month long. So applying a steady or a gauge analysis that provides a steady peak flow is pretty appropriate at that point. And then for the hydraulic modeling, I tend to jump to a 2D personally on my first go, and that's mainly because I'm a younger person. I've been in this industry for 5 years. I actually learned 2D before I learned 1D, so it's actually what I'm more efficient in. But that's definitely not necessarily the case. It depends on model to modeler as well, and that's just my preference. But I tend to have a 2D model that is a little more coarse than what you would want at a design final design phase is essentially what I would say.
Great. And we have a question from Anders. When developing rainfall and flow amounts for various recurrence intervals based on the USGS and other data sets that might go back to like the 1930s, how do you account for an increased storm intensity and frequency associated with climate change? Do you increase it somehow, or do you just acknowledge that a current 100-year event is larger than one statistically estimated based on the old model data, or do you use a different method?
Yeah, so that's a interesting question. And I think it's, how do I put it? Again, it depends a lot of where you are in the project, of how you do that. I think early projects like feasibility concept level, I don't think it's as important to do those projected future flows or future precipitations. But once you get to the permitting level, it might be a requirement, right? And I would say using that RMAT tool, especially in Massachusetts, as guidance is a great way of doing it because it provides essentially a level of effort guidance for how you should approach it depending on what your project is. So an example of that is there are certain methods that when you perform these statistical analyses provide a confidence interval. Sometimes the easiest tier of level effort is just to use the 90th higher upper confidence interval for precipitation or for flow at that site. Another example is to use projected. So there's a bunch of complicated climate models out there is to download that data, perform your own statistical analyses on that, and that has a projected future precipitation that you can then plug into your uh, rainfall runoff model. And again, whether you do one or the other, I think should be guided by those RMAT recommendations more than by like my personal judgment. Um, I should also put out there that MassDOT has their own system for, um, I guess, for estimating future flows. So if you're specifically working with MassDOT, I would recommend looking at their guidance.
Great. Next question from Dave. He's heard the limitations of FEMA models. Do you agree that they're limited? And if so, how and what way?
Yeah, I mean, yes, FEMA models are limited. I agree with that. Essentially, a lot of them are very old, for one. There's an example project we had in Western Mass where the FEMA model was made in the 1980s, and the program that everything was run on doesn't, I can't find it anymore. I don't know how to use it. That is definitely a limitation, and it becomes an issue. That is one sense that they might be outdated. Another sense is that they don't have, I guess, the spatial resolution you would want for certain design um, parameters, for example. So again, in our example project here, we used the 1D like requested FEMA model to perform this no rise. But when we came to our final design for fish passage, for example, the cross sections in the FEMA model were way too far apart to properly assess that. So we developed our own 2D HEC-RAS model to look at very nitty-gritty velocities and depths in that channel. So I would say FEMA is very important because it is a regulatory agency. You definitely have to address it. But once you do, they generally don't have the spatial resolution you might want for a final design. So I'd always recommend, not always, sorry, but in general, I would say that we tend to make our own models on top of the modeling that we get and alter with FEMA.
Great. Oh, here's another one from Daniel. In contrast to surface waters, can you recommend any sources for groundwater flow models for withdrawals through public and private wells to promote an understanding of sustainable yield for groundwater?
Yeah, I'm gonna say, but I'm not an expert on groundwater. You can definitely email me after, and I can try and contact some folks I know in GZA who are a lot more expert at groundwater. I'd be happy to do that. My contact is here at the bottom of this page. Again, I just don't want to speak on it because I am a surface water person. That is my specialty. But I know there are public sources out there, and there are groundwater models as well that you can use, such as ModFlow, but I'm not an expert on them.